Yeah, everybody needs an internet persona, so I am Ken the Metal Professor, because I do heavy metal on the radio, and I'm a retired professor of math, and now I entertain myself by doing math videos. And it's that time of semester where, in the typical United States calculus sequence, Calc 2 students are very likely in the midst or just getting out of applications of integration, volumes and surface areas and arc length. And yesterday I made a video kind of going over a hint for certain surface area problems for solids of revolution. And today I'm going to take a look at arc length problems because they tend to give you headaches. Because when you go into the section asking you to calculate the arc length of a function from this point to that point, the function very often looks gross, okay? But what I want to stress is that they have to. They actually look gross for your benefit. So the typical arc length problem says find the arc length of this function from this point to that point. And the function usually looks bloody awful, okay? It has to, because if you know the arc length integral that you need to construct and then solve to find an arc length, it's horrible. And the suite of functions that we have that can produce a doable integral is very limited. And those functions oftentimes have to look gross when they start off. Now, if you've traveled to hotels, and I don't know if I've seen one of these recently, but up to a few years ago, you check into a hotel and go in the bathroom, and just to prove to you they cleaned it, there was this little really thin, like paper thin stripe of stuff around the seat. It would say sanitized for your protection. That is what these functions are. They look awful. They look like they would stink like a hotel bathroom, but it's for your protection. Okay, it's good that these functions look strange. So here's why, with an example. If you're watching this, you probably already know that this right here is the arc length integral. So you're given a function, you want to find the length of the arc of the function from a starting point to an ending point. You have to build the square root of 1 plus the derivative of the function squared, and then throw that in the square root. Did I already say square root? I think I did, but it's on the screen. It's not a double square root. One of the pitfalls that people tend to fall into, that I've seen over and over and over, is students like to just build the entire integral right off the bat and then carry around all this baggage, the integral sign and the square root, before the interior of the square root has been resolved. Okay, don't do that. Just worry about the inside part first, and that's where you're going to discover that the functions that you've been given to handle that look like they're from the devil are actually beneficial in their appearance. So here's an example. Find the arc length of x cubed over 3 plus 1 over 4x from x equals 1 to x equals 2. Now, you might look at this and say, what the hell is that function? This is not a function that we might normally mess with in typical problems. It's weird looking, especially having the x in the denominator over there, okay? But it's okay. So take a deep breath and do one thing at a time. Remember that we need to construct this integral here, okay? Don't stick on the integral sign. Don't stick on the square root until you've implemented the inside and shaken it out. So we're going to build this square root thing by working from the inside out. So the function, again, x cubed over 3 plus 1 over 4x. Its derivative, x squared minus 1 over 4x squared. That doesn't look much better. But here's where things start to get good. Okay, we do have to square it. And that looks gruesome, but this is just a kind of a binomial term squared. So it's the first term squared with the second term squared, and then 2 of the cross terms. Now check out the cross terms. Those x squareds are going to cancel. And so this term squared gives us x to the 4th. The second term squared gives us 1/16 x to the 4th, positive. And then one of the cross terms of these two terms is negative 1/4. The other one is also negative 1/4. Altogether, you get negative 1/2. And remember what we have to do with that. We have to add 1. And now we have a couple of constants that get together, and this is what it looks like. You might say, oh, that's that. You're going to throw that under a square root? No, thanks. Don't go to the square root yet. Because this factors, and it becomes something simpler, squared. And so when we throw the square root onto that, ta-da, we end up with a function that is now going to get integrated, and that's very easy to do. So ultimately, this problem boils down to the integral of x squared plus 1 over 4x squared. Integrate that, slap on limits of 1 and 2 and subtract, and you are done. And I'm sure you can handle that, so I'm not even going to do it. The story here is with the arc length problems, especially when the functions look gross right off the bat, don't panic. Build the integral from the inside out. Don't worry about the square root until you've simplified what's going to go into the square root, because that stuff might actually shake out as something squared, so that when you slap the square root on it, it's going to simplify. And maybe it doesn't become something squared, but very likely it's going to end up with something that simplifies that will allow for a pretty straightforward substitution when it's time to do the integral. And then when it is time to do the integral, don't even worry about the integral until you've simplified the square root. So it's not time to do the integral until the square root has been completely resolved. Don't drag around all that baggage on your paper until you actually need it. The point is that with the functions at hand, yeah, they're going to look terrible, but they're intended to provide a pathway through to a solvable integral, and that's why they have to sometimes look really, really gross. And that is my story about arc length integrals.